Okay, good afternoon, guys. We are at the last day of the value-added course. This is going to be the last technical session, and next session is going to be the industrial-based things where Nityanandam is going to take over the session. This is the last session of mine actually. So in this session, as we have discussed in the discussed on yesterday, that we are going to talk about the residual network, like we often call it as ResNet. So in this session, this slot, we are going to talk about what is mean by residual network and why it is becoming the improve. I mean, why it is getting its own. Yeah, why it is getting, what is the base of the residual network and why the booming has been done in the residual network and so things we are going to look ahead. So, before, just I need to recollect some of the topics that we have discussed earlier, like on yesterday. So that the neural network is nothing but a universal approximation, or let's say approximating function or approximator that can approximate any kind of function that has been given inside. So we have also discussed about the feed forward network. In that thing, how the hidden layers are being presented and how the connection is being done, and what is mean by activation function, what is mean by we have discussed about what are the optimization techniques that has been used there, and how the calculation are being done with using the matrix multiplication, like we have seen the sample sum of exclusive or, right? So the basic steps of those are will be traversing by when we go for the higher layers of networks like CNN or something like that. So those kind of stuff, like a very basic sense of a layer concept, and those will traverse along with us. So whereas if you see the okay, then we have seen about the convolutional neural network. We have spent a session for, spent a slot for that. So in the convolutional network, we have talked about how the convolution has been done, what are the different layers that are available in the convolutional neural network, what is the main key points over there in CNN, like parameter sharing and so stuff we have discussed about, and how the convolution layer is going to act upon, how the pooling layer is going to be act upon, and how the detection layer, let's say we have seen an example of ReLU, so how it is going to act upon. So these and all steps we have seen in the yesterday's session. So at the last session, we have talked about Google Net, which is one of the advancement, like it has been published in 2014, and we have seen how many layers would be there, and what is present inside that. And there we have talked about a new concept called the inception layer. So you might have seen about that one cross one convolution, and after that you have 3 cross 3 and 5 cross 5. After the 3 cross 3 and 5 cross 5, again it will be combined together. So these kind of stuff we have talked in the Google Net, and you have seen like a 9 inception layer in the Google Net, and then we have seen two more pooling layers in the pooling layers, max pooling layers in the Google Net. So these are all stuffs we have seen in the yesterday's session. So having that in concern, like we are, I'm saying that, I mean, I hope that you have gone through some of the things related to that, and even you have listened the lectures, so that we can proceed by with using those understandings with respect to the neural network. So before entering that, I just recollect one more thing with regards to the approximation function. Like a neural network is going to approximate any function that you are going to do. I mean that you are going to give as an input. So which means that you have even also seen the UAT, which is nothing but a universal approximation theorem, which is nothing but uh, you have seen that with given the number of layers and given the given the number of layers and given the correct activation function, or like correct activation function, then we can approximate any function that is real valued mapping function, like Bosel's measurable function. So we have seen about that too. So what is the thing that they're lagging is like there is a concept we have talked about, the depth of the model and the width of the model, right? So increasing the depth of the model, it will leads to one more problem called vanishing gradient, as well as we'll across with we'll come across with a problem called overfitting problem. So these two problems will arise when you increase the number of layers, and even if you increase the number of layers like 120, 135, like that, the training will become complicated. Like the complexity will become computational complexity will be very high. So we are much more concerned about those things. So in order to avoid that, we have come across with the CNN, right? So CNN, if you talk about in that perspective, even there is also some of the drawbacks in the CNN. So okay, having those kind of stuffs, we are going to come to the newer approach called residual network. So here you might come across with the residual in the complex integrals. In your first semester and second semester, you might have seen about the complex integrals, right? Or complex analysis chapter, you might have seen with the residues and the residuals over there. So here we are going to talk about somewhat general procedures in the residues, whereas in the maths you are going to talk about the integration. A lot many steps will be involved there. But here we are going to talk about some fewer steps. So but the thing is, inside the very beneath, if you talk about if you talk in the lower ground, everything related to the residues are the same. But now, here, since we have talked about in the higher terms, I just need to give you one introduction with respect to that. So, if you say residue, which is nothing but output minus input, right? So, this is going to be, we call it as residue. So, if you say, let's say I am mentioning residue as R of X and output as H of X, and input as X. Okay, so you are trying to calculate, what you are doing in the archetype scenario in the neural networks is, you are given with the X. Okay, you are given with the X, you are training your neural network to in order to achieve the output. Like H of X is where, as we have discussed in the earlier session, we could identify that this H of X, yeah, as we have seen earlier, this h of x is nothing but the output of the output, which can be taught or which can be identified from the data set itself. From the data set itself, we can identify which what is the output it should give for the particular input. So this is what the understanding from the h of x from the feed forward neural network or the convolutional neural network that we have seen already, and even I have insisted this point also. So from the data set point of view, if you talk about from the data set point of view, you can see that the data set can teach, or this can infer the neural network what is the last or the final output that we need. It cannot teach, or it cannot explicitly say what the inside or what the hidden layers should do. So we are having this concern, like, and now what we are trying to do is we are trying to form h of x is equal to, which means, yeah, in archetype scenario we are going to find the h of x. But if you come from this equation, what you will get is you will get r of x plus x. Okay, here if you say here the thing I need to convey here is, like, if you say this is the h of x, so some let's say I'm just giving an arbitrary example. It is not it is not, it won't, it won't give you the, it will give you the somewhat just, but it won't give you the entire concept that we are going to talk about. So I'm just giving a very mere and very basic example. This is also dependent on some of the constraints of the neural network also, right? Okay, now h of s, if you h of x, if you are, let's say x is equal to 2, and h of x you need is going to be let's say 15. Okay, Now, if you see that given input is 2 and h of x is equal to 15, right? So what you need to do, you need to make the neural network that so that if the x is equal to 2 is given as an input and h of x should be the 15. So let's say not in this case. Okay, we can say in this way. Yeah, now when x is equal to 8, you need to train your model or train your neural network in order to get the output as 15. So this is the case, right? So in this case, the entire neural network or the feed forward neural network will concern this two parameters alone, x and what is the h of x. Whereas in the residual network, this r of x will be taken into concern. So here the r of x is equal to this is going to be the I mean 15 minus 8 obviously is going to be 7. So in the residual network, what you need to do is you have to train your model to come across with the r of x alone. So you can see that by having the x is equal to 8, is it possible to come across, I mean, is it possible to go for 15 or 7? So you can see the difference that it is easier to go for 7 rather than the 15. So by having this in concern, here you can see that residue has a lower value. So at that occasion, this residue becomes easier one to calculate. So here you can see that apart from this, forget about this equation related to the core neural network. In the neural network, you are just concentrating on the h of x and x alone. Whereas in the core neural network, you won't, I mean, the feed forward neural network, you won't even consider the r of x. But here you are going to consider the r of x. Here, one more thing you have to notice here is the output is equal to the residue plus x, which means that residue plus the input value. So just have it in your concern, like output here, I mean, output is equal to residue plus x or plus input. Okay, so here your work is to train the model to to attain the residue value rather than the actual value. Okay, actual value or actual output. So this is the basic thing you need to understand from the residue. So the term residue, right? So okay, these have this concern in your mind, and then we will look into it, what has been there and everything and all. Now, here, if you see that, I think I have even I mean, I have even shown this in the yesterday session also. Here, this and all 2010, 2011 neural networks. Here, 2010, the Google Net is going to, I mean, come into existence, and in the 2015, ResNet with a layer of 152 layers. Okay, so if you use these kind of layers in the, I mean, use if you use these kind of layers in the normal neural network, it will get into two kind of problem. One is going to be the vanishing gradients. One is going to be the vanishing, even we will talk about in this, I mean, we'll talk about in the slide also. So vanishing gradients, as well as the second one is going to be the computation complexity. Even apart from this, we do have some other problem also. Like, okay, we'll start one by one. So here you can see that the residue network has 152 layers, and you can see that the accuracy is I mean, the error has been very low, like 3.57, whereas compared to the Google Net, it is nearly half a percent, right? So here you have an important term called a shallow network. So what is the shallow network? This is going to be the new term for you, because we have not discussed about this earlier. So the shallow network is nothing but it approximately having very low number of hidden layers, like single digits. So often it refers to the one layer. In the hidden layer, number of hidden layers is equal to 1. Often, I am not taking all the scenarios. Like, let's say I'm just giving a maximum scenario. Number of hidden layer is equal to one or probably two. Okay, so this is going to be the scenario for shallow network. So here you can see that ILS VRC, that is which is nothing but 11 and 2010 and 2011 based neural networks are having the very few layers. Like here you can see that there is two consisting of two layers. Okay, so this is how the entire scenario like progress proceeds by. Now, deep versus shallow network. What happens when we continuing stacking the deep layer or a plain convolutional neural networks? So 56 layer performs worse on both training and test error. So you can see that here in the training error, the 20 layer is showing the lower error comparative to the 56 layer. Even while incrementing the iteration, either error should be reducing. Yeah, it is obviously it is reducing. But the thing is, comparing to the 20 layer of CNN and the 56 layer of CNN, the 20 layer of CNN is giving the good result, whereas compared to the 56 layer. So this is one of the major drawback, right? So moreover, we have a current scenario that increasing the number of layers, increasing the overfitting, right? So, but these errors are not caused because of the overfitting. Yeah, yeah. Here even here also it has been mentioned here. So it is not because of the overfitting alone. So these kind have a problem like vanishing gradients and so on so stuffs are there with respect to if you talk about the performance degradation here. Now, the deeper model should be able to perform at least as well as the shallower model. So, we know that the deeper model will have the number of layers greater than the shallower model, obviously. So, a solution for reconstructing is copying the learned layers from the shallower model and setting the additional layer to the identity mapping. So, which means that here the thing is, uh, you can see here the deeper model, if you increase the width of not with actually depth of the model, yeah, if you increase the depth of the model, you can identify that the number of computation is often increasing, and then it will be very I mean it will be very time lag to train those models. So in order to restrict those, in order to have I mean in order to make it efficient, what we will do is we'll use the shallow model first, right? So we'll have we will train the neural network with one layer or two layer of hidden units. So first of all, we will train it, and then we will add this to the deeper model. So what happens there? You can see that the entire model will have the layers from the shallower model, so that the output will be increasing. So moreover, the primary thing why we are going for this kind of stuff is deeper models are very hard to optimize. Like the parameters, let's say you are having 152 layers of sorry, not fast, it is in the FFN, feed forward neural network. If you say 152 layers, if you have the third neuron may cause an error in the upcoming layers. You have to identify that, and you have to rectify that. So in that case, you have to use the forward algorithm, you have to use the back propagation measure and back propagation to calculate these things. And using the back propagation, if the width of the model is very high, then it is going to be another issue. So computationally it will be very high. It will making billions and billions of equations there, and it will make a problem further also. So we have talked about the number of computations in the previous case also, like how many billions and millions of calculations are needed for the layers in the Google net itself. We have Google net itself. We have talked about that. So because of that, because of having that in concern, we are moving it further. These kind of stuff like using the shallower model, we can update the layers of the deeper model, so that the efficiency can be increased without much more efforts, or without that much calculations that are needed for the deep neural networks. And you can see the convergence will become very slow if you increase the depth of the neural network. So that is also becoming one more issue. Deep neural network starts to degrade in performance, and vanish exploiting gradient may lead to the extremely complex parameter initialization to make it work. Still might suffer from vanish exploding even for the best parameters. So we have talked about the gradient descent algorithm also. So there we will come across with the vanishing gradient problem. And long training times, due to too many training parameters, obviously the training time will be increased drastically. So you can see that if you have, let's say, the same example, 152 layers instead of the ResNet, if we have any 152 layers of neural network, okay, FFN layer, if you have. Right. If you have 152 layers of neural networks, you can see that training those, I mean, for each neural network, you might have 20 or 30 neurons, like width of the training model. If it increase, then the parameters also going to be increased, which means that weight matrix will also increase. So in that scenario, you will get into a mess. Like it will, the training time will take an enormous time. So we cannot, I mean, we cannot offer that kind of scenario, like that kind of messy and very lengthy scenario there. So the partial solution for vanishing or exploding the gradients is batch normalization. Okay, I forgot to mention one here. So in the upcoming slides, we will mention it as BN. Okay. So here, if you say the batch normalization to rescale the weights over some batch, like so batch normalization is nothing but if you have a, I mean, let's say here, like if you say here I have a 8 layers or 10 layers here, after that you will, when you do the batch normalization, you will rescale the weights. Okay, so then it will become easier to calculate the further weights also, which lead to the smart initialization of weights, like example Xavier initialization. There are a lot many techniques inside this also. So this was also an important research problem for like batch normalization was also an important research problem. If you have time, you can look into the batch normalization problem, and then you can come up with your own model. So train the proportions of the neural network individually. This is all the solutions that you can give for the vanishing exploding gradients or vanishing gradients problem. And highway network is like adding the features from the previous time steps has been used in the various tasks, like the features that I mean, it's just like something related to the previous one. We are relying on the previous one. It's something related to like feedback. You can somewhere related to feedback, but it is not exactly the feedback is. And most notable of these highway networks proposed by, I mean, yeah. Here, highway networks feature residual connections. Residual connections have of the form y is equal to f of x plus c, and highway networks will have in the form of f of x into sigmoid of wx plus b into plus x into 1 minus sigmoid of wx plus b. So you can see that the weight function itself associated here. So you have to consider this highway network. So this is the mathematical notations that we have for highway networks. So here you can say highway networks enable the information flow from the past, but due to the gating function. Okay, so you can see that the time, I mean, the t parameter has been associated with here, right? So this is the archetype scenario for archetype mathematical model for the highway networks. So here comes our ResNet. So a specialized network introduced by the Microsoft that connects input of layers into the further parts of the networks to allow the shortcuts. So we call those, even I have mentioned here, so we are our neural network is to train the R of x, which means that we are trying to attain the residue value. Okay, and then that will be added with the input. So input is nothing but the way beyond the input layer, right? So this input layer will be connected to the output of the residual layer. So that what happens, it will be directly attained there. So you can see a jump over the residual block. We will talk about that in detail. So the simple idea is that great improvements with both performance and training time. So you are just going to skip out some layers, then you are going to join there. That's all. So here you can see that it is a plain neural network that you can see. You can see those calculations in even yesterday also we have talked about this. Like G is nothing but the activation function, and A of I mean A of L plus 1 is the layer output of the layer 1, and A of L plus 2 is the layer output of the layer 2, and you have seen about this. So I don't want to dig into the same here. Now I am just going to the crux, like residual blocks. So if you see the residual blocks, this is going to be the plane connection. So you can see that in the left side, you can see the plane connection. One layer is connected to the another layer, either can be a fully connected or it can be a partially connected, the sparse connected things that we have seen before. So it can be like that. But whereas in the residual connection, what it will be there is, it will be directly, or a connection will be it will be parallel to the neural networks, and then it will be connected to across some of the layers. Okay, so in this occasion what you will get is, here you can see that here you can see that z of L plus 1 is equal to WL of L plus 1 plus A of L plus Z L plus, I mean B power L plus 1, and here is going to be the G of Z power L plus 1, and L plus 2, the second layer's output is going to be dependent on the W A of L plus 1, which means that this output is completely dependent on the L plus 1 and B plus 2, B of L plus 2, which is this corresponds to the second layer. So, but whereas what happens there is, this will be directly from the input layer. So you can see that yeah, here you can see that you are having a direct input, like as we have told already, this is going to be the residual one, and then this is going to be the input. So relu on output plus the input. So here, instead of in this plane connection, what you will do is you will try to mimic the entire function by having the layers alone. Whereas here in the residual connection, you just need to form the residue, that's all. You don't need to worry about the, I mean, you no need to worry about the actual function's output. It will be taken care by the X parameter. So you are just splitting your jobs. It's kind of splitting your job. So the types of residual network, if you have original network or original residual network, will look like this, like input. After that, you will have weight, and then batch normalization, and then you will have relu, and then you will have weight function, then batch normalization. The final one is going to be addition, and then followed by the relu activation or relu detection. So here this is going to be Bn after addition. So after this addition, right, addition step is there. There we will have the batch normalization, and here is going to be relu before addition. Like instead of having this relu at the bottom or relu at the last, the relu will be added further, and you will have the addition step at the last. Even this has a one of the, I mean, this has one of the important application over there. We'll discuss at the last. And here relu only the pre-activation, like this has been shifted much more ahead, like here at the starting itself there will be an relu followed by the weight and followed by the bn and relu weight bn. So here what happens is full pre-activation, like instead of activating at the last, like bn at the last and relu at the last, the entire thing will be shifted to the first itself. So whenever the data comes in, that batch normalization will be done, and then it will be handled with the relu, and then weight followed by the bn and followed by the relu and followed by the weight and followed by the addition. So these has one of the important thing, like the last one is called as relu next, I'm sorry, rest next. So we have talked about ResNet, right? So the current scenario is dealing upon with res next. Okay, so this is the thing we are latestly coming upon with ResNext network, which is something similar to the last one. So skip connections, like we have seen about the skip connection, right? X identity, we call it as identity layer or identity. I mean, identity scenario or whatever we can use, the word we can use. The thing over here is, like we are going to indulge into the skip connection. The skip connections are also called as shortcuts. So such connection are referred as skipped connection or shortcuts. In general, similar models could skip over several layers also. So as I have told already, your ultimate target is to achieve the output Whereas for achieving the output, you are going to use the value of residue and the input layer. So for getting the input, you are going to get it from the X itself, and for getting the value of residual, this network is going to be taken care. Okay, this residue is going to be taken care. So in this location, after fine tuning, you have to tune your network to produce the correct form of residue, instead of you are training your neural network to produce the correct form of output. Rather than here again, I'm insisting, rather than approximating the entire function, it is going to approximate your residues alone. So using those residues, you can identify the actual output of the function using the input function or input values. Okay. So DA refers to the residual part of the network as a unit with the input and output. So this block that has been mentioned before, right? So this is called as the this is called as the residual block. So in this scenario, what happens there, as I told already, instead of calculating the entire, or instead of approximating the entire function, you can see that you can see that the residue is going to be calculated from the neural network. So such residual part receives the input as an amplifier to its output. So here again you can see the same technique like image signal processing we are doing, right? The same technique you can see it here, the amplifier. Okay, so input is going to be the amplifier for the output. Another option is to use the projection to the output space. Okay. So which means that you are going to directly project the input space to the output space. Either way, no additional parameters are used. Okay. So what happens there? You don't need any additional parameters like any W or the weights are not needed here. So nothing is needed here. Just going to plug in the X, which means that input. So the new model, which is nothing but referring the original residual function h of x. So residual parts now fits to the new function like f of x is equal to h of x minus x. So here you can see that h of x plus x is the original mapping in recast into. And hypothesis of our research is that it is easier to learn the f of x. As I told already, so having this format h of x is equal to r of x plus x. So r of x is going to be the approximation or the value that you need to get. So you can approximate easily, because these two will be the x value and r of x value will be somewhat nearer, and so you can easily calculate that. So theoretically the problem is equivalent. So exactly. So I have shown you the derivation. I have shown you the step difference, right? So how it has been derived from the normal neural network regarding this. So ResNet as a convolutional net. So till now we have talked about the fully connected layers, whereas the residual idea could easily expand into the convolutional neural network. Other adaptation of this idea could be easily introduced to almost any kind of deep layer networks. Like not only as a convolutional neural network, you can expect. You can make it happen in the ANN, or you can make it happen in the FFN also. So the ResNet archetype, ResNet's archetype architecture is going to be something looks like this. Here you can see the residual block is being placed here. So here we are talking about the stacked residual blocks, and even every residual blocks have 3x3 convolutional layers with ReLU activation. Even you can find the ReLU activation, ReLU detection. So here you can see the composition that this is not fully displayed. We'll look into it. Okay. And then here you can see the periodically double of the filters and downsample spatials using the stride 2. So we have even talked about this in the previous sessions, like how to how the downsampling and the stride 2 is being taking place. So that's why the slash 2 is nothing but the downsampling rate. So now, so here you can see that additional convolution layers are added in the front. So you can see that very next to the inputs, you can see the additional convolution layer has been done before the pooling itself. So this is you have to understand there. And next thing is going to be no final, I mean full convolution layers besides FE1000 to output classes. So there is no another layers in between that. So I mean, yeah. Now here you can see that total depths of 34 and 50, 101 or 150 layers for the ImageNet. So this is going just I mean we have minimized this. That's what it has been mentioned here. Nothing much more details over this. So ResNet architecture for the deeper network, ResNet 50 plus use the bottleneck layer to improve the efficiency, similar to Google LeNet or Google Net. So which we have seen that in the Google Net we have two things in parallel. The first thing is one cross one convolution. Second thing is going to be the max pooling layer. After max pooling layer, we will have one cross one convolution, and in the one cross after one cross one convolution in the first parallel thing we will have three things like 3 cross 3, 5 cross 5, and 1 cross 1 again. So after this everything will be combined and we will come up with the fully connected thing. So similarly we have this thing like 1 cross 1 convolution followed by the 3 cross 3 convolution again followed by the 1 cross 1 convolution. This input will be directly connected to the directed across the 1 cross 1 convolution. So you can see that here the only purpose of the neural network is to find the residual. So Google, I mean ResNet 50 plus is using this architecture or these kind of layers, like this kind of layers is called as bottleneck. So here you can see that 1 cross 1 convolution, 64 filters to project that 28 cross 28 cross 64, whereas 3 cross 3 convolutional operators only 64 feature map. Whereas in the third thing you have 1 cross 1 convolution, 256 filters projects back to the 256 feature maps. So 28 cross 28 cross 256. So it has been shrunk to 64 and then it will be elongated or it can be expanded to the 256. So since we are input is going to be 256 and output is going to be 256, so here we are just making the tunnel. I mean we are just making the tunnels with a I mean, very low like 64. So that's why it is called as bottleneck layer to bottleneck layer. And this is I mean this is three different things. It has been projected there: VGG 19 and 36 layer plane. This is going to be 34 layer plane neural network, and this is going to be the 34 layer residual neural network. So you can see that there is a connection like two convolution layer, there will be a skip connection, and you can see the entire scenario over here. At the last you will have the average pooling technique. Okay, average pooling technique will be there at the last. And next thing is deeper bottleneck architecture, right? We have seen about this in the previous case, like in the right hand side we have seen about that that first it will be 1 cross 1 and then it will be 3 cross 3 and then it will be 1 cross 1. So whereas in the left side you can see the 3 cross 3 followed by the 3 cross 3, there is no 1 cross 1. So you have to understand that here also we need to understand input is going to be 64 dimension, where here it is going to be the 256 dimension. Okay, addresses the high training time for the very deep deep networks, keeps the time complexity same as the two layer convolution, allows us to increase the number of layers, allows us to model the converge much faster. Like the deep bottleneck architecture will reduce the complexity, I mean computation complexity much more, and it will allow us to increase the number of layers also, and the convergence is going to be very fast. The 152 layer ResNet has 1.3 billion flops. The flops is nothing but the floating point operation. while whereas VGG 1619 nets has 15.3 billion to 19.6 billion flops. So here you can see that having the 152 layer, we are having only the 11.3 billion flops. So as I told already, the flops is nothing but the floating point operations. Okay. So why do ResNets work well? So having a regular network that is very deep might actually hurt the performance because of the vanishing and exploding gradient. So we have discussed about this. In most cases, ResNets will simply stop the improving rather than decrease in the performance. So you can, I have discussed about this in the notepad itself, like why it has been showing the greater things, greater achievements. If the layer is not useful, L2 regularization will bring its parameter very close to zero, resulting in A of L plus 2 is equal to G of A of L plus A of L. So when using the ReLU, so you can see that if the parameter of the if those layers are not very useful, the input and output are going to be the same. So there will be no degradation, or there will be no outlier will be there. Okay, so in order this reduce the that kind of ReLU, and as well as that kind of inactive layers also. So you can see yeah, all these sense will show the greater achievements or greater efficiency while doing the ResNets. So in theory, ResNet is identical to the plain networks, but in practice, due to the above, convergence is much faster. Okay. Due to the above, the convergence is much faster. No additional training parameters are introduced, no additional complexity is introduced. So here we are just going to give the connection in between them. So the training is for not for the output, but the training is for the residual values. So training ResNet in practice, the batch normalization after every convolution layer. This is going to be the important point. And Xavier tool initialization from HETL. This is the paper, the citation that we usually do. So SGD and SGD plus momentum, this is nothing but a gradient descent plus momentum, and learning rate is going to be 0.1 divided by the 10 will when validation error plateaus, and mini batch size is going to be the 256, and weight decay is going to be the e power minus 5. No dropouts are used. I think you have seen the dropouts in the Google net, but here in the residual network we don't have any dropouts. So loss function, if you talk about the loss function over there, so if you see the loss function for measuring the loss of the model, we are going to use the cross entropy and softmax. So here also we are going to use the cross entropy and softmax. So the output of the cross entropy was normalized using the softmax function. So which means that the cross entropy will give you the error value, and which the softmax will do the normalization over there. So if you talk about the result of the entire things like in the ResNet, so you can see that about to training very deep neural networks without degrading. Like we have 152 layers in the ImageNet, which means that we have 152 layers of neurons, and we can train those networks without any degradation. Deeper networks now achieve the low training error as expected. So here we have talked about in the linearly connected or normal connected layers like FFN, increasing the depth of the layer might increase the error rate. So whereas in this case, increasing the deeper networks achieve the lower training errors. So this is what we have expected to happen. So and so here as we have seen before, this residual network has achieved the 3.6 percentage of misclassification error. So it is better than the human performance. So even it is showing the better better than the humans, and And here it has been shown in the 2015 competition. It is shown what are all the things that has been projected over there. So ImageNet classification, which is nothing but ultra deep, which has 152 layers of networks. And ImageNet detection, which has 16 percentage better than second. And ImageNet localization, which is 27 percentage better than second. And COCO detection 11 percentage, and COCO segmentation has 12 percentage. So, I mean, these are all the tracks like classification, detection, localization, and COCO detection and COCO segmentation are being considered. And after considering all the things, and then it has achieved like a residual network with the 150 layers. It has achieved the first place. So now, comparing the plane to the residual network, like we are going to compare the, first of all, we are going to, in the left side image, we are going to compare the 18 layers are connected, normal plane networks, neural networks are connected, and we are going to get the accuracy or misclassification error rate, and then 34 layers. Okay, so in this you can identify, in the left side of the image itself, you can identify the lower the depth, higher will be the accuracy. Here you can see the lower error rate, right? So 18 layers shows the lower error rate, and 34 layers shows the higher error rate. So we can identify that lower the there is a threshold between that those things, like between the layers, number of layers, there is a threshold. But considering that threshold, lower the number of layers, higher will be the accuracy. So that has been true in the case of plain neural network. Whereas in the second case, if you see here, you can see that higher the number of layers in the residual network increases the performance. Like the residual network with the 18 layers shows the higher error compared to the residual network with the 34 errors. So even you can see you have to mind this also. Like during till 5 iterations, the 18 is dominating rather than 34. But after the 5 iterations, you can see that 34 is dominating. And you can see the dropouts has been occurring at the same place. Okay, this all happens so now we are going to talk about the test error. So we have talked about the training error. We are going to talk about the test errors. Like here, we are going to consider the plane 20, 32, 44, and 56. So it has been, you can visualize what has happened there. Here you can see that the 20 layer shows the lower error rate, whereas higher layer like 54 layer shows the higher error rate. So even you can see that after the iterations of I think three, the bottom is iterations. After the 3 iterations, it is multiplied by 10 actually. So after the 30 iterations, or let's say 3 units of iteration, we can say 3 units of iteration. So after the 3 units of iteration, you can see the drop in the error rate. So, but whereas in that scenario also, you can see that the 20 layer shows the lower error rate, whereas 56 shows the higher error rate. But you can see one more thing, identification you can see there. So if you compare the 56 layer and if you compare the 44 layer, the error rate is very huge. Whereas if you compare, the error deviations are very huge. If you compare the 20 and 32, you can see that after some time the error between, or the I mean marginal difference between the errors are being very low. Okay, so you don't have any much more gap here. So it shows that both the layers are going to give you the same. Even you can see the actual rate is going to be the same. So this is why I told that there is a threshold, and that threshold will act upon here. There will be a problem there. So in another case, you have to think it in another way also. Increasing the number of layers will increase the weight parameters, and then it will increase other problems also, like vanishing gradients, and so on. So stuff will be increased. So we have to keep that in our mind. Next thing is here, this is nothing but the ResNet framework. Like you can see that ResNet with the 110 and ResNet with the 56 and ResNet with the 44 is showing the nearly the same performance. but you can see that increasing the number of layers will increase the performance. So it can be greatly identified over here. So I mean, so you can identify those things here, like increasing the layers, it will increase, even that too has some limitations. Okay, and this is the train error with the residual 110, like 110 layers, and the residual 1202 layers. Like in that case, what happens there is 110 shows the low error, whereas the pink one, the violet or whatever the shade you can say, that shows the higher layer, higher error. So 1202, this is also the thing I told you before, right? So increasing the number of layers also has the threshold. So after that convergence or after the threshold, the error will be increasing. So that has been explained over there. So ResNets on more than 1,000 layers, like we have talked about the 1,202 layers, right? Here, to further improvement of learnings for extremely deep ResNets, identity mappings in the residual networks, this has been proposed by these authors, suggest to pass the input directly to the final residual layer. Like you can see, even I have talked about this in the previous slides, like here the input is directly down to the last layer, and there you will be it will be added with the residual block. This is called as residual network, and this has been added here. So input will be directly linked to the directly coupled to the very last layer. Okay, here you can see that in the first two things, you can see that you have a relay activation at the last, whereas in the last three you don't have anything kind of like that. The input will be directly connected there. So that is what we mentioned over there. Sorry. So that is what we mentioned over there. So hence allowing the network to easily learn to pass the inputs as identity mapping both in forward and the backward passes. So these are all things. Here you can see that even I have talked about this. So even this is the image that I have placed over there. So instead of having the relu at the last, we can have the fully pre-processed or pre-activated inputs. So here you can see that batch normalization and the relu activation or relu detection will be at the present or at the first itself. So here ResNet 1001 and 1001 proposed, original one and 1001 proposed. So you can see that the performance is very high, like training loss is very low, and you can see that accuracy will be the test error. If the test error is low, and you can see that accuracy will be very high. So so this will leads to the increase in the performance. Like even we don't have any relu at the last.
ఏ నాన్ సిజిబిఏ క్రెడిట్స్ 3 ఉంటాయి. ఆ క్రెడిట్ 5 రోజులు కోర్స్, ఇది 5వ రోజు.
So now next thing, this is related to the I mean this is
ఏది
related
మేము
to the
కోర్
backward and forward
పేరు
passes. So the YL is going to be the forward pass, and whereas this is the last one is going to be the backward pass. So we have since there is no time for looking over the back propagation networks, we could not identify this. I mean we could not talk about much about the back propagations. So now improvement of CAFAR 10, it is nothing but the newer one, the next to the ResNet, and this is related to the ResNet 1000. So participants, I request you to mute your volume, I mean mute your mic so that no one can test it.
పక్కన రా.
Yeah, now here you can see that the CAFAR 10 is the advanced one in the ResNet. This is also coming under the ResNet 1000. Here you can see the performance, like it has been added with the pre-activated functions. Like we have talked about the batch normalization and the relu activation at the start itself. So if we do that, the efficiency is also increasing. So reduce the learning time with random layer drops, like dropping a layer during the training using the full network in testing. So as I have told you about this, when the layer is not important, that value will be assigned with 0. So the entire input will be taken, or it will be it will be traversed to the consecutive layers. So if you consider if you consider the consecutive or sequence of layers, you can identify that when the layer is not there, or it is not important, it will be made as value nearly equal to zero, and then the input, due to the shortcut or the direct link of the input itself, the input will be traversed to the next layer. So using that, it will make the it will make the rest it is making the ResNet effective. So the residual blocks are used as the network building blocks. So instead of having the normal neural networks, they are using the residual block. So during the training, the input flows through both the shortcut and the weights. So, and then in the training, each layer has a survival probability and it's randomly dropped. Okay, so the survival probability is one of the another thing you have to notice upon, whether the layer is to be there or not. That probability will show like that, and depending upon this, the layer will be assigned with the values. So testing all blocks are kept active and recalibrated according to its survival probability during the training. So as I told already, it will be calculated. The weights will be calculated depending upon the survival probability. So now we are going to talk about the wide residual networks like ResNext. So now here you can see that the accuracy of the inception V4. So here we are going to include inception also, like we'll talk about one by one. So ResNet plus inception. So inception model, we have discussed about this in detail in the yesterday's session at the last slot, how the inception layer will be. So if you combine the residual network with the inception layer, it is showing the higher accuracy, like 80% of the accuracy. So this is one thing we have to we have to consider, and this has been analyzed in the year of 2017. Now there will be things changing also. So here VGG, the highest memory, most operations. Okay, this is with respect to the operations versus the accuracy graph. So VGG shows the highest memory and the most operations. Whereas here Google Net, or here the operations are very minimum, but the accuracy is somewhat to the level of nearly 70%. Whereas ResNet 18 is at the level of 70%. Whereas the Inception V4 is showing the higher, is showing the higher accuracy, like 81%, as we have seen in the graph bar chart. And comparatively, the computations are very low. Okay? If you see the even yeah, if you see the AlexNet, which is the 2010-2011 neural networks, you can see that the computationally it may be high, even the accuracy also increasing. So I think this is the one of the efficient graph that can portray the entire things. Like increasing the operation, it will increase the efficiency. So it is giving that kind of relation also. So here Google Net, and here we have AlexNet, the smaller compute, still heavy memory but lower accuracy. So now we are going to talk about the wide residual networks. Wide residual networks show the power of these networks is actually in the residual blocks. So which means that the wide, in the sense like width, is going to be increased. So number of residual networks in the layer is going to be increased. So it can be shown that I mean, it can be shown that the power is with respect to the residual blocks rather than the layers. So it is worth noting that the training time is reduced because of the wider models take advantage of the GPUs being more efficient in parallel computations on large tensors, even though the number of parameters and floating operations has been increased. So we have discussed about this too. The GPUs will be used for the calculations, because you know that for the GPUs, like graphical processing units, for the graphics we need to perform many parallel computations. Even here also we need to calculate many parallel computations. That's why we are using the GPUs over here. So using that we can attain the much more we can attain the more efficiency. So here the basic version is convolve 3 cross 3 followed by the convolve 3 cross 3, whereas bottleneck is going to be 1 cross 1 followed by the 3 cross 3 followed by the 1 cross 1, whereas basic wide is going to be the 3 cross 3 followed by the 3 cross 3, but you have a large number of residual blocks in the single layer itself. So wide dropout is going to be the same wide with but there will be a dropout inside that. So which is nothing but the rest next network. I have talked about this, right? So rest next. So residual connections are helpful for simplifying the new network's optimization, whereas aggregated transforms lead to the stronger representation power. So aggregated transform is nothing but y is equal to x plus sigma t of x, where y is the output. Like you can see, instead of having this, we are going to have that wider networks. Okay, so this is what the entire scenario talks. I mean, entire rest next talks about. So here you can see that there is a totally 32 paths are there, and here you have I mean here you have the adder at the last, and then here you have the concatenation, and then you will have the 128 I mean here you have the another layer. After that only you are going to get this. So and last one is going to be the normal ResNet. So here you can see grouped convolution, and second one is going to be block equivalent implemented as earlier concatenation, and A is going to be the aggregated residual transformation. So if you compare the rest next networks, it shows the even more higher accuracy, which with the lower error rate. So which shows a very lower error rate like this. It is nearly tending to lower than nearly 10 percentage. So you can identify much more efficient. Even I think even the machines can become more brilliant at this stage. So yeah, this is the CAFAR 10 model with respect to the ResNext architecture. So you can see that the same thing, the lowerment of the error rate. So here last one, 16 cross 64 is yielding nearly 3.56 percentage of error rate. So this is going to be it is going to be the overview that one cross one convolution. Sorry, one cross one convolution. If you have this is going to be the next few coming slides are going to be the just gist of the things that we have discussed in the last session. I mean yesterday's class, that 6 cross 32. It will be do with the 1 cross 132. It will yield like this. So next thing we are going to talk about. Yeah, these are not okay. No problem. Yeah, this is going to be the inception neural network that you will have a 28 cross 28 cross 192. It will go the 1 cross 1. It will go to the 3 cross 3. It will go to the 5 cross 5, and then it will go for the max pool also. Then it will be added at the last. So I mean, so this is what the inception model that Google Inet is using. I mean, Google Inet is using, and then the computational cost. You need to know. You have to understand about this computational cost also, and then yeah, network in network. So we have even this is nothing but the micro network, like MIP con layer with micro network with each convolution layer to compute more abstract features to the local patches. So the micro network uses the multi-layer perceptron, 1 cross 1 convolution layer, the precursor to the GooglyNet and ResNet bottleneck layers. It is this philosophy, like network in network, is arrived from the arrived from the GooglyNet. So we have told that identity mapping is nothing but mapping the input directly to the output, and it will show the higher, better performance. We have seen that justification over there, and this is the wide residual networks, and this is the aggregated networks that we have seen. So okay, I'll just show you the gist of this course. I'll just give you the gist of the course, and then we can wind up. So the first thing, in the first day of the session, we have talked about the image processing. So like various kinds or various dimensions in the image processing. So for basically, if you need to enter the computer vision domain, you need to understand what is the basic image processing, why we need this, why for any process like object detection, what are the layers needed, what are the basic process are needed. Then only you can come across with the designing of the modern concepts like neural networks. If you come to the neural network, you have to understand what should be done, what the process exactly should be done. Then only you can come for the exact things like how many layers you need, what are the dimensions of the layer, and what is the width and depth of the neural network you need. So these kind of stuff can be determined only if you know the basics. So according to me, the one mantra can help everyone, that if you know the basics very well, you can face any complex problems, like anything. You can face any complex problems in that industry or in that particular field. So from the start itself, we have talked about the filters in very detail, the mathematical perceptions of the filters, and understanding those mathematical perceptions are very mandatory if you need to design the new kernels and everything. So why we are making you to, I mean, why the industry is making or it is forcing the students, or forcing I mean, forcing their men or women who are working in the industry to learn the maths. Like for every problem, we cannot rely on the same solution. Like if you are going to have a image classification only for the cat images, like only for the images of cat, then you don't want the ImageNet kind of stuffs. You don't need that kind of calculations at all. So a simpler network can arrive at that place. So you have to you have to know, or you have to acknowledge how to, I mean, you have to acknowledge how to process that, or how to design that layer. So that is very much basic mandatory things. So okay. Apart from this, if you talk about the industrial perspective, like we have discussed about the self-driving cars, what are all the things, what are the functionalities that should be covered, and where the CV has been taking place there. And I think third day's first slot we have talked about that, and even more healthcare problems also we have talked about. So if you are interested any research problems, like you can ask any of the persons from your college. And even if you want to tie up with Techsy Academy's research process, even you are most welcome to contact me. You can contact me using the mail ID hariharanwales@walesinfoway.com. And even if you do have any doubt, don't hesitate to ping me in this mail ID. So if you mail it, I will reply it back by within an hour, or probably within a day, so I can mail you back. So apart from this, I will post some of the materials in the classrooms. Stay connected with the classroom. Whenever I incur with a new kind of material, I will post it in the classroom itself, so that you can get knowledge about the CV more and more. And one more thing I need to add, I think you guys are at the initial level of your career. You are at the starting pathway of your career. So from now itself, you have to track your things, like we call it as TD. I mean, there is two things in industry, like TD and TDD. So what is the first TD is? TD is nothing but track down. So which means that whatever you are doing, you should have a complete disciplinary idea. Like right from, you should have what you are going to do, why you are going to do, and in which way you are going to do, and so on, so steps like A to Z of the idea should be in your hand. You should document it. The document deserves that much of information. I mean, that much of importance there. And next thing is TDD, which is nothing but test driven. So yeah, test driven deployment, we call it as. So forget about the deployment and all, just have a test driven case alone. The thing is, like whenever just assess your progress. assess your progress in the short period of time, like monthly assess or 2 months assess, like assess yourself, like whether you are going in the correct way, whether your gradient, that means like your rate of doing is in the correct way or not. So just have that assessment and then go by. So right. I think we are at the end. So, and next session will be at the 3:30. That will be handled by the Nityanandam, who is the CEO of NIFOS system and has nearly 15 years of experience in this industry. And even you can, I mean, you can get lot many inputs, like industrial inputs from him also. So stay in contact with the mail ID, Harian Wales, and even if you want to engage in some of the personal course, like in my personal training courses under me, even you can contact this mail ID also, techzyacademyhv@gmail.com. So you are availed with, or you are having a lot many opportunities, and you have a lot many opportunities to work with, and you have a lot many opportunities to learn with also. So don't waste your time and keep the time productive, and make yourself like strengthen in the area that you are going to work on, like in this stage at the first year and the second year of the bachelor's degree itself. Choose what you have to do. So entire society is on your hand, is on your side actually. So you can do whatever you need. Even I personally suggest everyone to do like parallel courses. Like there is a UG diploma courses that gives you a strong base for your mathematics, like analysis, statistical analysis in the universities like IGNO, and even in the some of the open universities are giving the UG diplomas. So if you have any time, you can pursue the UG diplomas over there. After completing your BE, don't wait for like don't if you not wish to study in the PGs, like I mean, if you not wish to study in the colleges, you can go for the PG diploma. That is going to be the online course. You can take it anywhere at any time in the world, so that you can go for that. Even you can complete that. There are a lot many opportunities available. Search for that and make your life very beautiful. Okay. So we'll try to meet on the next time. Let's see. All the best, guys. So if you have any doubts, you can just mail me and I can reply you back.